Hi everyone and welcome to this channel. I hope you have an excellent day and I'm very glad to see you. This will be a crash course on similarity search. Similarity search algorithms are widely used in practice, especially in vector databases and in situations when you need to perform a fast search across millions or even billions of embeddings. This is an important topic to master for machine learning engineers and data scientists. In this crash course, we'll cover different algorithms along with the Faiss library, which is a Python open source library containing efficient implementations of indexes allowing to perform similarity search. And with that said, let's get started. This video will be related to the first part, where we'll be talking about kNN and inverted file index structures. First of all, we need to understand what's the idea behind this similarity search. Imagine that you have a query. It can be a text, an image, a video, and you have an embedding model that you use in order to convert this query to this embedding. And then on the right, you have a database. Again, it can be the database of text, images, videos, and you use that embedding model to construct this set of embeddings. The goal of the similarity search is to be able to answer, given the query, what's the most similar embedding from the database in relation to that query. And of course, you can use various implementations. The naive implementation is just to check linearly all the embeddings from your database, but of course it's going to take lots of time. And the idea behind the advanced similarity search algorithms that we're going to look at is to be able to do it much faster. Because imagine that you have a database of millions or even billions of vectors. Of course, you want to be able to find the answer in production much more rapidly. Okay, so if you know the basic machine learning, I think you are familiar with some of these similarity metrics that can be used. This is just as a reminder that you can use different metrics to measure the distance between a pair of vectors. So on the left, you can see the name of the metric along with its formula, and on the right you can see the visual explanation of how this metric works. This is just as a reminder. And now it's time to talk about the kNN, which is one of the most known traditional machine learning algorithms widely used in classical machine learning. Well, imagine that you have your dataset objects that are depicted on the left. Then you have a query, this black point, and what you basically do, you calculate distances from a query to all the objects. And then you, based on the distances that you've got and on the metric that you chose from the previous slide, you get the nearest neighbor and you return this as an answer. And of course, as I said, the problem with this algorithm is that it performs literally linear search, and you have to, in order to get the answer, you have to look up for all of the possible neighbors, and it takes a lot of time. Now this is a chart representing the performance of kNN from different viewpoints. First of all, we can see that it achieves always 100% of accuracy, which is completely logical. You iterate through all the possible options and you choose the best one. Then regarding this training speed column, you can see that it corresponds to 100% performance, which literally means that there is no training phase, and you don't need to spend any time for training kNN. This is just one of the most interesting points regarding kNN. But then, as we saw, it performs linear search, so its inference speed is very low. There are no optimizations in terms of memory, and as we will see in the future, there are algorithms that allow you to compress the vectors so they take less space in the RAM. And given that, we can conclude that there are mainly two application scopes for kNN. The first one, when the dataset size or the dimensionality of embeddings is relatively small, and it allows you to ensure that computations remain fast. And the second one is when you absolutely require to have 100% of accuracy. So in this case, kNN will be the best choice for you. Otherwise, it's strongly recommended for you to use another algorithm. Now it's time to talk about the Faiss library, about which I talked earlier in this video, which contains various implementations of similarity search algorithms in Python. And it uses the term index, which designates a data structure implementing a particular similarity search algorithm. In this example, we can see that we create an index using this structure we call the constructor of index flat L2 class. Here the L2 means that we are going to use the Euclidean metric. And another option that you could have is this index flat EP. EP stands for inner product. So basically you have only two options regarding this algorithm. And then you use the method add, where you pass the data containing a list of your embeddings with a specified data dimension, 256 in our case. And then for the inference, you specify how many nearest neighbors you want to search for. For example, here we only search for the first nearest neighbor. But for example, if you specified the parameter 3, then you would retrieve this one and this one. So here we specify 3, and then we call the search method, where we pass list of embeddings for which you want to find the nearest neighbors. And then, of course, with the parameter of how many neighbors you want to search for. And here we'll retrieve two variables, D and E. D will contain distances to the most similar neighbors, and E will contain their corresponding indexes from the data that we have passed here. And the flat suffix also indicates that the dataset vectors are fully stored in the index. To estimate how much space each vector would take up in this data structure, we just need to multiply 4 by D, which means that every single component of a vector requires 4 bytes to be stored in, because it has a float data format. So given the fact that each vector has D dimensions, then you need 4 times D bytes. Given all that we have talked about, there are several ways to improve kNN. First of all, we need to narrow the search space. Right now, we are searching linearly for all the possible options, which makes kNN inefficient, or just to reduce the dimensionality of the vectors. With this way, calculation of distances between a pair of vectors will be faster. And it's also worth noting that when using either of these approaches, we will no longer perform an exhaustive search, which is good from one point, but we need to understand that such algorithms are called approximative nearest neighbors, because they no longer guarantee that our results will be 100% accurate. So in some sense, this is a trade-off between the accuracy of the algorithm and its speed. Now let's talk about a more advanced structure used as one of the implementations for the similarity search algorithms called inverted file index. According to the definition from the Wikipedia, it says that it is a database index storing mapping from content such as words or numbers to its locations in a table or in a document or a set of documents. To put it simply, let's look at the example from the diagram. Here on the left we have a set of indexes where each index points to a set of values from our dataset. What we want to develop is such a structure that will allow to take query as input, apply a hash function to it that will point to one of the indexes in this table, and then, given the mapping that we have between index and values, we will then point to a set of candidates that might contain an answer to our query. And then we will just perform an exhaustive search in this candidate space and retrieve the most similar candidate. In some sense, we reduce search scope. Instead of searching for all the candidates in the table, we only bound ourselves to, in this case, 3 candidates, which is much faster. One of the popular mechanisms that allows to implement this data structure is called Voronoï diagram. The idea of the Voronoï diagram, it tries to create a set of non-intersecting regions to which our dataset points will belong to. And to be precise here, each point from our dataset can only belong to one region of the Voronoï diagram. And each region has its own centroid which points to the center of this region. For example, here, here, here. The main property of Voronoï diagrams is that the distance from a centroid to any point of its region is less than the distance from that point to another centroid. To put it simply, imagine that here I have a point. What this statement says is that the distance from this point to the centroid will always be less than a distance from this point to any other point outside that region. So for example, here the distance will be longer than this one. This is a very useful property of the Voronoï diagram, and also Sometimes Voronoï regions are also referred to as cells or partitions. But I'm not going to dive into how Voronoï diagrams are constructed, but it is usually very fast. There exist mathematical algorithms allowing to do this. And we want to use Voronoï diagrams as this hash function that will allow to take the query and point it to one of the indexes in this table, which will then allow us to retrieve a set of candidates. Here's how it works. Imagine that we have a query point. What we do is that we calculate its distance to each centroid of Voronoï regions, and then we find the nearest centroid. So for example, in this case, we can see that this query corresponds to this nearest centroid in this green zone. And then if we imagine that this centroid contains several neighbors, then we just take every single neighbor in this green space and we calculate the distance to the query, and then we retrieve the nearest candidate. Very simple. We don't need to search for all the other neighbors in other regions, which is very efficient and very significantly reduce the search scope. It might seem like a very good approach, but there is one problem, which is called edge problem, which is a case when our query is located near the border of a region. And as we can see here, for our query, the real nearest neighbor will be here from another region, which is located also near the border. But our algorithm is not able to see this, and it will still search for the neighbors inside this green region, which is problematic. One of the ways to alleviate this problem is to set a parameter that will allow not only to search for one nearest centroid, but for several ones. In this diagram, for this query, we're looking up for the 3 nearest centroids, and for the 3 corresponding regions that we find here, this orange, green, and red, we will then perform search among these candidates and retrieve the final answer, which in this case will be this neighbor, which is correct answer. Of course, it will take a little bit more time, but again, it is a trade-off between time and accuracy. And despite the edge problem, inverted file index is widely used in practice, and especially in the cases when we are able to sacrifice a little bit of accuracy in our search results in order for them to become much more rapid. A very good example is a recommender system. When we have a set of movies, let's say that we have millions of movies that we can recommend to a user. Of course, we can use kNN, which will allow us to retrieve the best matching movie for a user, but it will take a significant amount of time. Instead of this, we can use inverted file index, and let's say that you would retrieve like the 5th or the 10th best result for a user, but the search process will be 20 times faster than kNN. And honestly, if I were a user, I wouldn't notice the difference between the first best recommended movie or the 5th one or even the 10th one. For me, it would be like still an excellent result. But what I would notice is that the search time would be 20 times much faster in the second case. So, which makes here inverted file index a winner. Speaking of the inverted file index performance, here we can see that in comparison to the previous diagram, we have slightly sacrificed accuracy, and right now we also need some training time in order to construct Voronoï partitions, but right now we get a significant boost in the inference speed as we don't need to go through all the candidates to find the nearest neighbor. We can just search for a small part of it, and as before we didn't do any optimizations with the memory, so it's logical that it stays at the same level as before. Now, speaking of Faiss implementation, it's important to refer to the term quantizer, which is an object that determines how the database vectors will be stored and compared. For example, in the case of inverted file index, here we use the same index as we created before for the kNN algorithm, and here it specifies how vectors will be compared, and they will be compared using the L2 distance. This is just one of the terms that is useful in the Faiss notation. And then here you create an index where you pass the quantizer along with the D parameter that designates the data dimension in the N list, which will contain the number of Voronoï partitions. Then we use the train parameter to create the regions as a pre-processing step. Similar to the implementation before of kNN, we use the add parameter to add the data. And what's interesting in this example is that we use the similar data parameter for the train and add methods, but in fact we could create regions on one set of data and then add data to it based on other regions. It's up to how you prefer. Both options are possible. And then for the inference, we specify the number of nearest neighbors for which you want to make the search for, and we specify the nprobe parameter, which tells how many Voronoï partitions we want to use to search for the candidates. And if you remember the example before, where I showed you that we expanded the search space to the red, orange, and green zone, there this nprobe parameter was 3. In this example, I specified it as 10. And then, as before, we use the search method where we pass the query and the k parameter, and it returns us the distances and the indexes. Similar to what we had before with kNN, we need 4 times d space for each embedding in our vector database. And then we need also to account for 8 additional bytes that will store information about the Voronoï partition to which each embedding belongs to. And with that said, this is the end of the first part. We have already covered introduction to similarity search and looked at examples of the algorithms such as kNN and vertical index. In the next videos, we are going to look at even more advanced implementations that will allow us to improve results. Thank you for watching this video until the end, and see you next time. Bye.